me. Okay, so I've sent a new note, right? Yeah. Phone. Okay, so we're gonna use that because there's a few changes. I've met with Tani before and she told me a few things that is wrong with the previous one. Okay, and she said sorry. So either way, let's move on. So today we're gonna look into heat equation. Okay, so heat equation is very important. So for example, let's say when we first turn on the aircon, okay, so the temperature here logically will be much colder than temperature over there, right?
Yes.
So that's what we're gonna study with this heat equation. We want to study what is the temperature of here. What is the temperature here, and when will the temperature will be equal all over the room. Okay, so that is heat equation. But for the purpose of this explanation, we're gonna look into this one. So in that book, it is a rod, cylindrical shape, and the sides of the rod, okay, for this part is what we call as perfectly insulated. So you know what that means? You understand this? Perfectly insulated? Okay, it means if we supply heat from the outside, for example, there will be no heat transfer across this material. It is perfectly insulated. The same thing from the heat from inside will not be transferred out. And secondly, this rod does not move. Okay. But the thing is, these two conditions is not what we call applicable in real life. So for example, thermos, when we tuang air in the thermos, we expect that the thermos is perfectly insulated. But when we pour the water 100 degrees Celsius, we open it back 12 hours later, it will not remain 100 degrees Celsius. So it is not perfectly insulated, but in this case we consider the rod to be perfectly insulated and also does not move. Also impossible. For example, if we place this thing on the table, so in engineering we call this, even though it doesn't move, but there is a micro movement that we cannot see. So movement is always there. Everything moves. So in this case, we consider the rod to be it doesn't move. Okay. Now you have got what we need. Okay, no. Close the book. We don't use the book. Before here. Okay. Now, for the sake of the study, we only care about this boundary. Because we want to study the whole thing, then we cannot study. So we study this, and I denote this as x1 and x2. And I supply heat here, and there is no heat supply over here, so this region logically will be much colder. So where is the heat transfer? The flow of heat must be what? From here to here or from here to here?
From heat to cold.
Yeah, from hot to cold. So this is the vector, right? And as I mentioned earlier, the temperature of here and here, is it going to be the same? No. So now our temperature U depends on where. Okay, where it is. So here is different, here is different. Okay, and it also depends on time. The longer you supply heat, the higher the heat in this region. Alright, so this is it. Okay, now everybody understand?
Yes.
Okay, it's very easy. Okay, now I want to talk about energy stored in this system. So energy stored in this system, logically, if we put so much heat and the heat loss is very low, what will happen? Temperature increases, right? What if the heat is lower and there is much heat is being flushed out? The temperature will be what? Cooler. So the total of energy stored here depends on how much heat is in, and we minus that how much heat it is out. Okay, everything okay? Now, just a little bit. Energy stored here, is it going to be constant? It is not constant, because with time there will be a change of energy. Okay, so we call that as a rate of change of energy stored is heat in minus heat out. Easy, kan? PDE is easy. Okay, so now we have two parts. Focus on this part first. I will derive this part first. Rate of change of energy stored. Energy stored is, now the energy in this region is ditentukan oleh, what we call it? Determined by the density of the material. Rho. It also determined by the C. Do you know what C is? We learned this in physics. Specific heat capacity. Remember that? So energy stored depends on density, specific heat, and of course our temperature. So far so good? Okay, so this is the total energy. Alright, but we have a region here from x1 until x2. We want all this. If you want to calculate all this, what we do is we want the total of energy stored from x1 all the way to x2. Okay, of all this. Rho, specific heat, and also the temperature. Okay. Alright. Energy stored. Okay, before I move further, remember we have d dt here. Okay, so we just put the differential respect to time, and not to forget this part. Okay, so okay, all right. So we move on. Rate of change of energy stored is, we can move this here. So what it will make is, what it will do, it will look something like this. Rho C, no D, del U, del T. This one is respect to X, sorry, I missed that. Dx. Okay, think here? Alright, so we have come to here. Now we stop, we pause. Now we listen to this one. Okay, so can I padam? Erase this one? Yes. See, the aircon does stop. So heat transfer is happening now. Okay, we need to introduction. Alright, so remember our heat in? Okay, I draw smaller diagram. This is x1, this is x2. Okay, this is heat in. So heat in is, what is heat in? Heat in is just, I introduce one new function, Q, at value of x1. Okay, Q is a function of x1 and also at the function of t. Okay, and what about heat up? So the only difference is just Q, but this time we have at this point. Heat up happens at x2, so we have Q of x2 and also with respect to time. So heat in minus heat out should look something like this. Q of x1 minus Q of x2. Okay, so now we are all set. Okay, I erase this. Okay. Good. Okay, so before I move into here, we can simplify this. Everybody remember fundamental theorem of calculus? Yes. No. Okay, never mind. I'll show you what fundamental theorem of calculus is. Okay. But I cannot explain everything in this presentation. But either way, we want to find the value of q from x1 to x2, and q1 minus q2, right? So difference. We have change of q over change of x over the region of x1 and x2. All this with respect to x. So this thing can be written as this. It was the same thing. Okay, so by fundamental theorem of calculus. Okay, so we stop here. Okay, what is this? Rate of change of energy stored. We have solved that to become like this. Okay, we will write that one. X1, X2, rho C del U over del T dx equals to heat in minus heat out. Heat in minus heat out we got here, and then we solve until here. So what we do, this one put here. We have x1, we have x2, del q over del x of dx. But I made one mistake. Here, what's the mistake?
X1, X2.
Okay, now if we do the integration, it will be 2 minus 1, right? This is 1 minus 2. So what can we do? Add negative. Okay, third. Understand? If you add negative, then we can transpose. Okay, so we need negative here. Oh, panjang ni. Okay. Okay, understand again? Alright. So x1, x2, rho C, del U del T dx. Good. Plus x1, x2, del Q del x dx equals to 0. Very good. This is the same integration. So what can we do? We combine together. So it becomes something like this. x1, x2, rho C, del U del T plus del Q del x equals to 0. Oh, very good, my student. Okay, now we are almost there. Relax. Okay, I erase this part. Everybody know how to solve this? No. You don't know? Okay, good. Okay, for example, this is an integration of something that equals to 0. Integration of something that is equals to 0. What is that something? It's not C. Because integration of C of dx, Cx. Right? The only possible explanation for this is that this something
Constant.
must be 0. Okay? Because integration of 0 is 0. Therefore, this part is 0. Now look here. Integration of this part is 0. So what can we say about this? The integral is what? 0. So now we have something like this. We have rho C del of U over del of T plus del Q over del X equals to 0. Okay. Now let's. This is when we get into what we call as Fourier's law. Okay, so if I want to explain this, it will take a long time. But either way, so Fourier's already tell us that this is a heat flux. Okay, we can find the definition here. Then del u over del x. This is a definition by Fourier's law states this. This is not proof. This is proof by empirical law. Do you know what empirical law is? So based on my research, Fourier's law is not derived by mathematics, but it is this law apply for most of the substance in the world. So most of the time we can use this, but there is also times that this equation does not valid. So it is an empirical law. Most of the time it can be used, and for this sake of purpose, if it is not applied, then we stop here. But if the law is applied, we can carry on, because we can substitute here. Q is negative k del u del x. Q we can substitute by this. So what happened? We have rho C del u del t plus del x of q. According to Fourier's law, q is negative k. Okay. I bring this over. Yes? Okay. Negative k del u over del x. Okay, so what happened? Let me simplify. Negative and negative. Positive. So we have positive k in front. Del and del u, we have del squared u over del x squared. This part we have del u over del t. Okay. Relax. Del u over del t, k, I bring this over, divide by rho c del squared u over del x squared. Okay, what is k divided by rho c? Okay, now open the notes, the new notes in the group. Okay, refer to what page? 4. Wait, let me check.
Yeah.
4 on top.
Okay, now remember this? Alpha square. Which page is it now? 4. Okay, now refer to page 4. It states that alpha square is equals to k over rho c. So from here we can simplify this. Del u del t, can we write something like this? U with respect to t. This one become what? Alpha square u double derivative of x. There you go. You know what this is? Heat equation. And that's it. That is the derivation of this small thing. So many words. And thankfully we arrived here. So this equation is very much helpful in the engineering world and also in this world, of course. So do I have any question? Not much the same as the Dr. one, but it works. Questions? Faham tak faham? Betul eh? Okay, bagus.
Any questions?
Okay.
Okay. So thank you very much. By the way, even though the heat equation is normally used for heat equations, but there's a lot of applications of heat equations that also involve, let's say, the traffic flow.
Okay.
Some researchers also recognize the traffic flow that
Comply the heat equation.
yes, they assume that the traffic means the vehicles are treated as heat transferred. Transferred from
tempat jam ke tempat tak jam?
is normally discussed on RAM. You know what is RAM? The RAM is after the tolls.
Oh, okay.
RAM. RAM out or RAM in. So sometimes we have to stop. Vehicles have to stop, isn't it? Before they can enter the highway.
Okay.
So the transfer is normally recognized as heat equation. Some people do recognize that traffic flow as heat equation. And that is what I've done in my research too with my master students.
So it can also use this form.
What? The traffic.
But it's not
It's not just traffic.
strictly just for heat equations. I mean for heat transfer.
A lot of things you
There's a
can
lot
do.
of
Yeah, you can discover that thing.
It's not only like heat.
Yeah. Okay.
But of course, we have to set the boundary conditions. There are different boundary conditions compared to the heat. Because
by the way,
for the heat, we have road, isn't it? Maybe other regions, but for the highway, there's a lot of the boundaries that we have to consider. We have the ramp, the sides of the ramp, as well as the main road and everything.
okay, betul. Saya nak sikit boleh. Okay, by the way, the derivation is for one dimension only. So why is it that one dimension? This is a very simple problem. Now imagine something like this. This is one dimension already long. If we have heat here and heat here, then it becomes two dimension. There's a lot of things need to be considered. And also, I didn't mention about the height of this. Okay, but the heat here and heat here will be different. Okay, but now we are doing one dimension, so we doesn't care about h. Okay, but in 2D and 3D equation, we need to consider all this. Correct? Okay. Next, I would like to call Arina.
Still in the same, yeah. Okay.
For the next presentation, I will present about the initial and boundary condition. Okay, so Izzul has talked about the heat equation just now. Or you can see at in page 77. 77. Okay. So heat equation is the one dimension. So the initial condition, we have to specify an initial condition so that we can solve the heat equation. Okay, so this is the first order of derivative since it is just t, right? Okay, so the t is we have only one initial condition. So in order to solve the question, okay, so we have to specify what is the initial condition. So the t is equal to 0. Okay, the initial temperature. Initial temperature at time t is equal to 0. This is time. Okay, so we can also write as u. This is the variable involved, x and t, right?
Yeah.
So equal to some function in interval x for Izzul x1 and x2, right?
Yeah.
But we can use x equal to 0 and L. Just L.
So is it x equal to 0 is initial point? Initial point?
Okay, position.
Position.
Boundary.
Yeah, boundary. So the boundary is, in terms of x, 0 and L. Okay, so the T is equal to 0. So this is the initial condition.
I think it is not correct if you start with u of x, comma t equal to f of x, because f of x is
Just a function of x.
just a function of x and is normally given.
Yeah.
It's the prescribed values. It is given when t is equal to 0.
Yes.
So you should not write u
Only-
of x, comma t previously. You should straight away put 0 for t.
Just
Okay.
Yeah.
Okay.
So I will learn about boundary condition. So in order to solve this heat equation, there are several questions you need to consider or the boundary question. So then you can turn to page 78. You can see there are some points. So I will explain to you about this point. So for the first point, how will the temperature change with position and time if the end of the rod were insulated? That means for this point, you have a rod. You have a rod. So in this, it says that the end of the rod were insulated. So that means the end, both of end of this rod were insulated. So that means there is no heat at this point and at this point. So for example, I have point x1 and x2. So there is no heat loss or anti-heat at this boundary, at these two boundary. Okay. For point number 2, what if both ends were held at a constant but different temperature? That means we have the same rod, for example, the same rod. It says that it has the both ends have a constant temperature but different temperature. That means if in this position and x1 and this position x2 we have constant temperature. For example, if we have at this point 50 Celsius and this point, for example 70 Celsius. What does it mean by constant temperature is the temperature will always be 50. It cannot change. So in this temperature at the second end will always be 70. So in this case I put it 70. So it will always be 70. But it is constant temperature. But the temperature must be different. Okay. For the third point, what if one end was insulated and the other was held at a constant temperature? Okay, for the third point is, this is the combination of these two. It's the two situations. So for example, you have a rod. One end we have a constant temperature and one end was insulated. So at this point, there is no heat loss or no heat. So this means at this point we have 0, and this point we have constant temperature. So whatever the temperature is, it must be constant. So that means if 50, also it should be 50, or it cannot change. Understand? Okay. For the fourth point, what if one end was held by a constant temperature and the temperature at the other end oscillate in time? Okay. This means you have a rod. So at the first end, x1 and x2, we have a constant temperature. So like say, for example, this is 40 Celsius, and this one oscillate with time. Oscillate with time means, okay, for example, for 30 minutes, you have 30 Celsius, and for another 30 minutes, you can use another temperature. So it will oscillate between these two temperature. So this is the four type. This is the four type of boundary condition that we will tell you later. So far you understand?
That one lah.
I need to do this. Okay, so for boundary condition, according to Newton's law of cooling, it says that the rate of heat from the object, the rate of heat from the object is proportional to the difference. Maksudnya is equal to the difference between the object temperature minus by environment temperature. So in our heat equation, in our case, the rate of the heat from the object is actually the heat flux. The heat flux that Izo mentioned earlier, that Izo use the symbol Q, but in the book it use symbol V. The heat flux, the rate of the heat from the object. So as we know, so we can put the equation of the heat flux that we have earlier. So equal to negative K del U over del X. This is the heat from the object is equal to this one over this one. Right. So as you can see in page 79, it gives us, it says that if the environment near X equal to L at constant temperature U2, that means that the environment near X equal to L, this is our object. At constant temperature U2, U2 is the environment temperature. So our environment temperature is U2. And our object temperature is U L of T. So this is, so we can just plug in the equation. We will get U minus U2. However, okay, as you can see, there is a H here, right? The H is the heat transfer coefficient. For example, why we need the heat transfer coefficient? Because this is our object, this is environment. Our object, for example, if we have a metal, the heat will transfer faster. But if we have a wood or anything, the heat, so this thing need to be considered in our equation because we are dealing with heat. So in this, at the heat flux, we have the big A. So the big A is for example, we have a road, then this is about the cross section area. So we will not always use the same cross section area, right? So maybe sometimes we have a bigger road. Okay, so we get the equation like this. So as you can see, at the second point, it gives it says that environment near X equal to 0 at a constant temperature equal to 1. That means the temperature, environment temperature is U1 and object temperature is 0. Okay, so the same, we will get the same. Del U over del X equal to H U, but our position is at X equal to 0 in time minus 1. Okay, so are you clear?
Based on buku ni, nanti tak ada yang bawah tu positif kan? Ke tak tinggal
Yang bawah tu tak ada. That's not negative because hit in. Kosong. Hit in. Hit out negative.
Ni at position 0. So we the end. So we got this. Okay, so we will see the first boundary. We will see the first boundary, that is Newman boundary condition. Okay, Newman boundary condition.
How many boundary conditions?
4.
One is Neumann.
They reach it.
Robin and periodic boundary. Okay, so we will explain about 4 boundary condition that specify the 4 group that I explained before. So for the first is Newman boundary condition. Okay, Newman boundary condition, it say that we can use this when we know the derivative. Is known. In our case, the derivative is the heat flux. So, for example, if we are given h equal to 0, we can we can solve this equation. For example, okay, we got negative k a delta u over delta x h equal to 0. So everything will be 0. So and then we this one to this side and this one to this side, we will get delta u dx. I forgot. Sorry, I forgot. This is L and T. Okay, so we will get this one. L and T is equal to 0. Okay. And then we solve for the second one. H equal to 0. This is for U, L, T. This is for U, 0, T. So we solve, we will get K, A, del U over del X equal to, so H is 0, so everything will be 0. And then we will get the same answer, del U over del X equal to 0. So our first section rule just now, we say if the boundary condition 1 and x1 and x2 is equal, the heat or the temperature is equal to 0, that means these two ends are isolated. So that means there are no heat loss or output energy at this end. No energies, but the heat loss, the temperature is equal to 0.
Does it necessary to be 0?
Yes. For this boundary, Newman boundary, it should be 0.
Bukan. Dia constant. Derivative tu yang 0.
Derivative 0. Derivative 0, not this one 0. For this boundary condition,
Pada balik yang kosong aja selesai.
maksudnya untuk ni derivative ni non. Maksudnya derivative non ni dia kena kita cari dia kena dapat kosong. Maksudnya kalau kosong tu baru dia apply untuk Newman boundary condition. Sebab Newman boundary condition dia kena dua-dua ni adalah dekat dua-dua n adalah kosong. Kalau kita dapat benda lain, maksudnya dia bukan Newman, maksudnya dia akan
Okay. It's not that the temperature here is 0. You don't know the temperature. U of xt, you don't know. But the thing is, we know that change of U in temperature with respect to x, with respect to position, is now 0. Okay, so means our U now does not change over x. Means degree temperature here is the same now. Because change of U, change of temperature with respect to change of position, x is position, is now 0. So we can now say that temperature here, and here is constant because at the end both of them are insulated. So there is no in previous case heat in and heat out, but now there is no heat in, there is no heat out. Everything is insulated. Everything is within this rod. So everything here is respect to x. Over time, there will be an increment of temperature, but the temperature all over the place is the same. Okay. We consider this to be no heat loss. But insulated, so heat cannot go anywhere. Okay.
So do you mean that the Neumann boundary condition should be insulated?
Both ends are insulated. Both ends.
It's not necessary. The Neumann boundary conditions means that we prescribe the boundary so that it is described in terms of derivative. The derivative value del x is not necessarily to be 0, but if it is 0, it means that the rod is insulated. But it can be that value del x equal to something else. Let's say equal to 2.
So if it is equal to 2, then there is heat flux.
Yes.
Okay. So not perfectly insulated. Either way, heat flux is something like this. You understand heat flux? No. Okay. If heat flux is 0, means that there is no heat transfer. Heat cannot go through.
Yeah.
If there is,
Stay forever.
let's say this is 80% insulated, then there is heat flux. Heat flux is 20%. 20% heat loss along the transfer. Understand heat flux? Good.
So the Neumann boundary condition is more general than
Derivative.
the
Okay, sorry. Next.
You again?
You don't want Arina.
No. Only 3 presents.
Wow.
What is doing? Just sit here.
Wow.
Okay, the first one is Newman. The second one is
Differential.
Differential boundary
Condition.
Okay, for Dirichlet boundary condition, the value of the full okay, for Dirichlet boundary condition, the value of
It is Dirichlet. We call it Dirichlet.
Dirichlet boundary condition is when the value of dependable variable is given. Okay, for example, okay, for Newman, there is no heat flux.
The derivative is known.
The
That one,
the
dependable variable.
okay, no. So then it's given that the heat is heat transfer. Okay, there is heat transfer and okay, okay. For in this case, the dependable variable for heat is temperature. Heat is always involved temperature, right? Okay, so the temperature is given. Is given at some position. In this case, for this x to 0 and x to L. so the temperature is given at this position and this position. So it is noted as this is the x position is 0, so 0 here and t u1, and this is also L T u2. Or in other words, for example, we give this temperature 30 degrees Celsius, and this is 50 degrees Celsius. But it is always consistent, the constant 30 degrees Celsius. And this is, for this position, it is constant 50 degrees Celsius. That is Dirichlet boundary condition.
Dirichlet and Neumann, not Newman.
And no?
Neumann.
Neumann.
Nah, tu kawan kau.
Finally,
Lazy
So I will present about the Robin boundary condition. No. The Robin boundary condition is the combination from the two type of Dirichlet and Newman's Neumann boundary condition. So.
And sometimes it is called mixed boundary condition.
So for the Robin boundary condition, I already told you. This is a combination of dependent and derivative.
Derivative.
Okay. So my friend already told you about the dependent depends on temperature. Derivative.
Then
Del U.
okay.
Del X. Okay. So
What
the
do you mean by T there?
temperature.
We normally use U for temperature. T is for time.
U.
Tim sao dia.
Okay, U untuk U for the temperature. So to make you understand. Okay. From this picture, we know that the condition is insulate, right? In derivative insulate, so the depends is dependent. Sorry. So I will tell you about the Dirichlet condition first. So the initial And so the Differential condition told about the insulated condition. So the Newman. Sorry, this is about the Differential.
Pronunciation.
Ini untuk Newman. Betul.
Okay, so combination of these two is that from the previous one. For example, this is example. Let's say this is x0. This is x1. This is x2. Okay. So for the dependent variable is temperature. It means that the temperature at this point is known. This is boundary condition. So this temperature U at this point x1, respect to dependable on time also, is known. For example, denote that as U1. Okay, and at this end, the derivative. When we see derivative in heat equation, remember it is a flux. Now we know that del U over del X, the flux is given. It can be 2, it can be 3, or it can be 0. In the book, we use this and this as an example. But the thing is, it can be U1, can be anything. This is also, it can be constant or whatever. So in this case, we use 0. So if we know the initial condition, we know the temperature here, and we know the heat flux here, therefore it is Robin boundary condition.
And it is not necessarily to be constant as well.
Yeah, that's why 0 boleh, fx pun boleh.
S1, S2 and everything.
Yes, apa baca?
Okay, betul. Nak tanya tu lagi.
Okay. Okay. Habis dah?
So the periodic boundary is the used when the physical geometry of interest and expected flow pattern and the thermal solution are of periodically repeating nature. It has the advantage to reduce the computing time.
Kau nak baca macam tu, please. Yeah.
What does it mean? Can you please explain?
Yeah, I'm trying to understand it.
By the way, for the numerical experiments or numerical calculations, for the Neumann boundary conditions, it is not unique. It is not unique, and Differential is unique. So for the Neumanns, even though it looks like quite easy, but in reality, it's very hard to solve. Normally, we have to use. We are trying to use a numerical approach, but numerical approach is quite hard for the Neumanns, but Neumann boundary conditions. There's a lot of method to prescribe the Neumann's the Neumann problem so that it is unique, but it can be done. It can be done. Okay.
That's why I listen in the internet and you could hear this.
So before we can understand, you need to know what is y, because y is not mentioned.
Dalam buku baru dia kena buat. No worry. Relax. Sometimes given derivative, sometimes given constant, sometimes given temperature. Relax. Just take the given solve.
This is actually the easiest example. In real life, there's a lot of
Yes.
variables involved, especially in the conditions of the region. If you have the road can be can have one material and they have another materials over here and they have another material over here. So it means that we have variable in terms of material as well. So the material itself is not a constant. So that is what we as researcher should look at. Instead of just this heat equation. But this is actually
Perfect
the
condition.
best example to explain on the heat equations.
Yeah.
Okay, so thank you.
Right.
Good luck.